Hello, in previous video, we explored the eye optical system purely from optical perspective. For example, for the cornea, which is the first surface of our eye, our optical system that we consider our eye is a kind of optical system, that we consider it as a lens that has two radii of curvature. One is the front side, the back side, and it's not completely spherical. We explained that why it's aspheric, how you can actually by two numbers you can define a aspheric surface. And for the refractive index, for the material in between, I explained that we use refractive index and Abbe number for those kind of elements in our eye. For example, for crystalline lens, it doesn't have a constant refractive index. The distribution is like gradient. At the center we have higher refractive index, at the edge it goes to lower refractive index. And for the center of our eye, which we call it vitreous chamber, that is full of liquid, and the refractiveness of that liquid is pretty close to water. So I explained all of those things purely theoretically, but right now in this video, and all of those numbers based on a lot of research, I find those papers and I explain them based on Brannan and Leo model, which is one of the good models for our optical system. Right now in this video, we're gonna use all those knowledge and import it into Zemax, and we can have a good simulation from our eye optical system. The main reason that we're gonna do this kind of simulation that is because the simulation of our eye is very important, because in a lot of optical system, like for example microscope or riflescope, binocular, monocular, all of these optical systems, we directly look at that optical system and the image plane is the retina of our eye. So if we're gonna optimize the whole system, we need to consider that optical system into our model. So our eye is a part of that optical system. And the other reason, which is very important also, in ophthalmology, that is a science that the doctors, how to take care of the eye, how to measure the different aspects of our eye. In ophthalmology, we have a lot of optical devices that we use for examining, for example, the surface of the cornea, the retina, all of these surfaces. So in order to do that kind of examination, we need to send the light through our optical system and get reflection, for example, from retina or any part of our eye. And by analyzing that data, we can see is there any damage on retina or something. So the optical model of our eye is important from that perspective also, because it's a completely black box optical system that we need to examine any kind of part of that optical system. So from these two perspectives, it's very important to have a good simulation. So all of the number that I'm gonna put in Zemax, in the previous video I explained where those comes from, the papers. I spent a lot of time on that. But you can go to Zemax website and there is an optical model of our eye. You can take a look at those numbers also. Those are exactly the same, and you can use either of them. You can but those numbers particularly, but the Leo and Brannan model is a very well known model that I'm going to use those numbers for this simulation. The primary one, let's go to is okay, here in Zemax, let me make a new file completely from scratch. So as I always said, the first step, I have another video about a tutorial how to get a start in Zemax. As I always said, we start with System Explorer. So the first things is the aperture. As I explained before, the aperture of this top of our optical system is the pupil of our eye. So we cannot put any input aperture for the whole optical system. So in this case, we're gonna select float by stop size. So it means that the optical system find the aperture, and all the aperture size is based on that point. So we're gonna select this one, and the the clear semi diameter of the stop is gonna be the aperture of our system or stop of our system. It's very complicated in image space. We call it, I think, input aperture and exit aperture in the image space. In object space, we call it input aperture. So, but for now, just select float by stop size in Zemax. The next thing is the field. For our eye, as I explained in another video, we click on open field. Our eye, we have a point in our retina that we call it fovea, that you have a lot of nerves that's very sensitive. In order to see a very crisp and sharp image, the focus should be on fovea. And as I explained before, fovea is 5 degrees from the center in nasal direction. You know, this is Y direction, this is X direction. So for that, I'm gonna put 5 for the angle, press enter. Okay, that's my field. So based on angle, yeah, angle, radial, okay, cool. Now let's look at wavelengths. So for the wavelengths, we cannot optimize our optical system based on only one wavelength, because we can see variety of colors, and all of those colors we have some chromatic aberration, but you know, we need to optimize it for all of them. So for the wavelengths, we click on settings and we select FDC visible, which is the optimum wavelength for visible light that starts from blue, red, and in the middle we have green. So all those lines are visible lines. So you select it as preset. We click on preset. So wavelength 1 is 0.48. Wavelength 2, 0.588, which is pretty close to green. And the last wavelength is red. So the primary one is the middle wavelength. So we don't change anything. So that's from the wavelengths. For environment, temperature, everything is okay. Polarization doesn't matter. I'm gonna skip all of those things. For material catalog, you know, right now the catalog that we are using is shot for glasses, but we need to, because you know we're gonna use different materials, we're gonna add miscellaneous, MISC, to this catalog. You click on this and then click on this arrow. So right now we have this material added to our catalog, and the rest not that important. And the unit is millimeter. For the lens unit, we use millimeter. So right now, let me close this one. This is our lens. Let me click on, actually I think it's better to see it this way. Okay, so let me put it here that you can see it better. Okay, so the object, stop, and image. So for the object, I want to put it at 1 kilometer. 1 kilometer is equal, each kilometer is 10 to the power of 6 meter. But in Zemax, everything is based on millimeter. So I'm gonna put 10 to the power of 9. So I'm gonna put 10 E9. 1 E9 actually. 1 E9. E9 means 10 to the power of 9. For the object, which is at infinity for our optical system. So that's the object. But because, you know, when you put object at very far distance, then, you know, your Zemax is gonna get really big. So in order to avoid that, I'm gonna add another surface after this. And for the comment, we can put beam, and we can put, let's say, 10 centimeter from our eye, which is 100 millimeter. So I put 100 millimeter for that. And here we plot from surface 1, which is the beam, to the last surface. So let me put it back. Okay. So the first surface after, you know, 10 centimeter from our eye is our cornea. And you remember in our previous video, I explained it, what is cornea. So for the comment, I'm gonna put cornea, and the radius of curvature. You remember for the radius of curvature of the first surface? And for the radius of curvature, you remember in the previous video, based on a Leo and Brannan model, R1 is 7.77. So for 7.77, and for the thickness, as you remember, I said it's not that thick, so it's half a millimeter. 0.55 is 550 microns. And for the material, as I always said, we use the model. So you click on material, after you select model, and for the index, we put 1.376, and for the Abbey number, we put 50.23. I have another video that I talk about Abbey number and the refractive index. So this is the Abbey number. For the clear semi-diameter, if you look at your eye, it's about 1 centimeter, it's 10 millimeter. And based on a lot of research, they use exact, for this clear semi-diameter, they use exact 5 millimeter, which this is semi-diameter, means the radius of that aperture. So we're gonna put 5, which, as I said, we should multiply by 2 to find the diameter. Mechanical doesn't matter. For the conic, actually for the first surface, I explained this concept also. It's not a spherical surface, it's an aspheric lens. It's not completely spherical, so it has some deviation from a spherical. And for asphericity, which is the Q parameter that I explained on that video, is negative 0.18. So I'm gonna put that number. The rest, we don't need to change anything actually. So the next surface after cornea is so we have cornea, and the second surface after cornea is aqueous, because between the cornea and the stop there is a liquid that I explained in that video, that it's like a jelly type material. So I'm gonna add another surface here. I'm gonna put AQ for this surface, and the radius of curvature of that surface, as you know, in Zemax is like this. You have one radius of curvature and the thickness, and now the thickness of this surface is gonna be the second surface, the second side of the cornea, which is 6.4 for surface 3, and the thickness is 3.16. The material, again, we're gonna solve it, we're gonna put model, solve based on model, is 1.336, and the Abbey number, is 50.23. So we're gonna use those numbers. And for clear semi-diameter, again, we're gonna put 5, and the rest for conic asphericity or conic in Zemax, I'm gonna put negative 0.6. So all of those values is based on Brannan and Leo model that I explained it before. So the next surface after that liquid is the stop, which as I always said, stop is, so let me double click here. Yeah, we have 10 millimeter from here to there. By clicking on the middle mouse, you can move. But the way that it's showing, I don't like it, because I can see the edge of the lens. You can click on settings and then hide lens edge. So click OK. So right now, pretty nice. This is the first surface of the cornea, second surface of the cornea, the liquid in between, and now we're gonna put the stop. And for the stop, as I mentioned before, we put pupil, and the radius of curvature, because we consider as a flat surface, we put infinity. And for the thickness is 0, because as I said, it just acts like a stop of our system. For clear semi-diameter, for the stop, it depends on the amount of light that we have in our environment. When you are in a very bright environment, your pupil gets smaller because you don't want to send that much of light. So the diameter goes to 2, I think. But when you're in a dark room, goes to 4. So based on, a lot of articles, 2.5 just for average between, actually this is clear, sorry. This is clear semi-diameter, so 1.25 is equivalent to 2.5 as a diameter. So I'm going to put 1.25, and mechanical doesn't matter. Conic is nothing. The only thing that we need to add, because inside of that hole there is a liquid, and that liquid is the same. So we're gonna put, for the select from model, refractive index 1.336, 50.23. Okay, so right now we have a stop. So now this is our optical system. When we put the stop, you can see the beams. So this is the beams, and this is the stop of our optical system. The next surface after the stop, actually for the stop, based on Brannan and Liu model, which is a very acceptable model, the stop of our optical eye is not completely at the center, or the center of our eye. It's about 0.5 millimeter deviated to the nasal direction. So for that, we click on stop, go to properties, then go to tilt decenter, and make sure that for after surface, click on reverse this phase, because in Zemax, if you change something, it's gonna be all the surfaces gonna change to that value. So for the X value, we're gonna put negative 0.5. Okay, so that's the stop of our optical eye. Now for the next surface, which is the anterior surface of the crystalline lens, or the front surface of crystalline lens, which is, if we consider exactly after a stop. So I'm gonna add another surface here, which is, we can put any name. So I'm gonna put front lens, because most of the people just call it lens, not crystalline lens. So this surface is not a standard surface. As I explained before, the refractive index is not constant for the crystalline. It has a gradient. So for that, we use gradient 3 in Zemax. And I have another video that I explain what are those. So gradient 3 for that surface. The radius of curvature of that surface, which is surface 5, we put 12.4. And for the thickness, you should be very careful. This thickness, the lens is like this. The thickness is from that curved surface to a virtual flat surface in the middle. So for that, this is the half of, not exactly the half, but into the virtual flat surface in the middle. So I'm gonna put 1.59 for the thickness. And for the clear semi-diameter, you can put any number because your system is limited by stop. So I'm gonna put 5. Now this part is a little bit tricky. For the N0, we should put all those numbers here. N0 is 1.368, which is the average of refractiveness at the center. NR2 is 1.978 e to the minus 3. NR4, we are not going to touch it. Then we go to NZ1, which is 0.049057, and NZ2 is negative 0.015427. So now let's discuss it a little bit before going to the next slide. So when you look at this model, NRY actually NR2 is negative 1 point. I will explain, yeah, why it should be negative. Because as I said, NR is like, because our system is symmetric, it's like NY. So as I said, the refractive index of the crystalline line is higher at the center, and when you go to the edge, it decreases. So NR is a coefficient for that, going from the center to there. If you look at the equation, so NR should be negative because, as I said, the refractive index is decreasing. But for NZ1, this is the linear increase of the refractive index in Z direction. It's going high because you are starting from the edge to the center. And NZ2 is Z to the power of 2, which is a negative value, comes from fitting to the actual value. So that's all the parameters that we need to put, actually. So the next, right now you can see this is the front surface of the crystalline lens. Now the next surface, I'm gonna add it after this one. Again, we're gonna use gradient 3. Okay, so the same thing, put 5 for the clear semi-diameter. The rest is not that important. N0 for surface 6 is gonna be 1.407. This is the refractive index at the center. As I said, you start from small value, you go to higher value. You started from 1.368. Now we are at higher value, so it's 1.4 at the center. We have higher refractive index. And then NR2, we can guess that it should be exactly the same, because in one direction it cannot be from the center. When you go in Y direction, it should be the same. Negative 1.978 e to the power of 9.78 e to the negative 3, and and NR4 0, we don't need to be worried about that. And NZ1 with 0, just NZ2, which is negative 6.6.05 e to the negative to the power of negative 3. Sorry, 6.605 e negative 3. Okay. So that's the what happened. Why it's not getting updated? Maybe last surface 7. Okay, let me see. There is something wrong. So gradient surface 3, radius of curvature. Yeah, it's infinity because we need to add another surface. The thickness of this surface is 2.43. Yeah, that's because of the thickness. Okay, right now we have, this is the half of the lens, but the refractive index is a function of those numbers that I put. So right now the next surface after the crystalline lens is we call it vitreous chamber, because it's like a chamber full of liquid. And it should be very clear. In that video I explained that why it should be very clear, because we don't want to have any scattering. So it has a liquid jelly like material. So for that I'm gonna add another surface, but it's gonna be like a regular surface. So let me put a comment back lens. For this surface, let's put it, let's put chamber. So the radius of curvature of this surface is the radius of curvature of our crystalline lens, which is negative 8.1, and the thickness, it should be very thick because as I say, it's from front to the retina. So the thickness is 16.23883. That's the thickness that scientists reported for that part of our eye. Actually, they have a very good method for that measurement. I think they use ultrasound wave that goes to the retina and get reflected from the retina, and by that measurement we can have a very precise measurement. Maybe that's the reason that we have a few digits after 0. So clear semi-diameter, we put 5, the same. And for the material, as I said, it's like water. Most of our eye is like a watery liquid material. So we model it 1.336, and Abbey number is 50.23, and semi-diameter is 5, and conic is 0.96, is very close to 1. So okay, this is a cornea. And now the last thing that we need to actually model is the retina of our eye. But our retina is not like other CCD, it's not flat, it has a curvature. And the reason that it's like a curve shape, because we don't have any distortion. If all the CCDs was like completely curved, then we could have better optical system. So for the image, for that surface, I'm going to put retina. And for the radius of curvature is negative 12. And for the thickness, it's nothing. Area is nothing. And for the clear semi-diameter, we're going to put 5. And yeah, actually the system is at focus. So if you do it exactly like me, you should get the same result. You can take a look at, let me start from the first, move it a little bit by a little bit, that you can see it. You see the optical system at focus. And Zemax also, if you go to the website, everything that they explain, they have those numbers there. But if you look at that and my PowerPoint in the previous video, you can get a better understanding of all those values. So right now you can see the beams. Actually, let's look at it from different angle also. Change it manually here. I want to see XZ actually. Yeah, you can see the fovea is here, so that's the main part of our eye. But you can see because of the pupil, we have some beam that are clipped. So if you go to ray aiming, and for ray aiming, you select paraxial, then this issue right now, let me don't do that, let me put it off. If you go to aberration, analyze aberration, and go to pupil aberration, yeah, you can see it's very off in X direction. So in order to resolve that, you click on framing and then paraxial. Then you can see we can put it back, and when you look at the beam in YZ direction, now we don't have any vignetting. So click on OK, and the system is at focus. We can take a look at the, for example, the standard spot diagram, make it a little bigger. Now we're gonna compare it with Airy or diffraction limited, so you know it performs really well. And one other parameters that we can take a look is MTF of our eye. So let me, the maximum frequency of our eye that we can see is 10 per line per 100 line per millimeter. So I'm gonna put 100. That's the for eye 20 out of 20 at the best distance, at the best age and everything. So when you click OK, let me actually add the diffraction limited also. So you can see the MTF goes to 50 at this value. So after that, we cannot see it very well if you go higher than 100. So yeah, that's the optical model of our eye. Maybe in the next video, we can combine it with any other optical system, and I can make it a little nicer, make it closer to the eye. Even visually, you know, we don't want to change anything, but you know, for example, if I right now it doesn't look like eye, but for the retina, let's say for the mechanical semi-diameter, the radius of curvature is how much? It's I think it was -12. So if I put -12, it's gonna make it like a curve. So let's put 12. No, let's put 5 for this one, and for the clear semi-diameter, let's put 12. So 12 for, yeah, you know, we can make it like a curve shape, like our right now is closer to our eye. This is the retina. This is the retina. This is the vitreous chamber, liquid crystalline lens, pupil, and retina, and here we have another liquid in between. Thank you very much for your attention, and the references that I use, I use all the references on my previous video, and also, as I said, the Zemax website also, they explain how we can model our eye optical system also. Thank you very much.